Hello, today I'm going to talk about Anova. We start with one way, Anova, and Anova means analysis of variance. It's an extension of t-test to more than two groups. If you remember our example with mice, where we had both English and Scottish mice and we measured body weight, now we extend it to Welsh and Northern Irish mice as well. We have four groups instead of two. The null hypothesis of Anova is that all samples come from populations with the same mean. All the means are the same, which is very similar to the assumption in a t-test, but extended to four or more groups. You already know variance as the square of standard deviation. It is used to represent the spread of data around the mean. In a more general form, we can write that variance is the sum of squared residuals divided by the number of degrees of freedom. And in case of variance, this is n minus 1. The core idea of Anova is to compare variance within groups and variance between groups. And in this figure, variance within each group is shown here by the black arrow bar, and variance between groups is shown as a gray arrow bar. The variance within a group is simply created by random sampling. In contrast, variance between groups, this one, represents difference between biological conditions. These differences could be due to random noise, in which case the variance between groups would be similar to the variance within groups, as illustrated in the left panel. Alternatively, the difference between groups, between biological conditions, can be due to real change. And then the variance between groups would be larger, would be in excess of random noise. How do we calculate these variances? We find residuals in each group with respect to the mean of this group. The mean of each group is represented by the colored horizontal line here, while individual residuals are presented as gray lines. The variance, as given by this generic formula, is the sum of squared residuals, the sum of squared lengths of these gray lines, divided by the number of degrees of freedom. And we can present it as a simple formula here at the bottom. This x bar G represents mean of a given group G, like this. And x Gi is the measurement number I from group G. This is the residual square, and then there is a sum over all groups and all individual measurements. This is the sum of square residuals. This is the number of degrees of freedom. This is the size of each group minus 1, just like in t-test, n minus 1. This variance, this within groups variance, estimates the common variance, sigma square, which is an unknown population property, regardless of the null hypothesis, whether null hypothesis is true or not. This is only internal variance in each group. For our UK mice example, the numbers are shown here. This is the sum of square residuals, this is number of degrees of freedom, and this is the variance, 17.5. In order to find the variance between groups, well, we have to be a little bit more clever. The formula is the same. It's the sum of squared residuals divided by the number of degrees of freedom. To make it comparable to the variance within groups, we have to find a residual for each data point separately. The residual is the difference between the group mean, represented here by the horizontal colored line, and the ground mean. This is the mean of all data points, the dashed horizontal line. Each group contains as many residuals as there are measurements in it. And the sum of squared residuals is found by this formula, is the sum of lengths of these gray vertical lines, just the same as in the previous figure. This is the mean of a group minus the ground mean squared and multiplied by the size of a group, because we have several residuals of exactly the same size. This is the number of degrees of freedom. This is the variance between groups, and it estimates the common variance only when the null hypothesis is true. The numbers are as follows. The variance between groups here is 208. This is something I mentioned at the end of the last lecture, the F test, which is the test for variance, for difference between variances. The test statistic is shown here, is the ratio of two variances. So we calculate a variance within groups, variance between groups, and calculate the ratio of them. And this ratio, this F statistic, is distributed with F distribution and these degrees of freedom, nu B and nu W. If null hypothesis is true, if there is no difference between groups, then we expect F to be close to 1. In our case, the ratio of 208 divided by 17.5 is 11.9. The ratio is quite large, so we suspect that in this case, the null hypothesis can be rejected. And in order to do this, we need to find a p-value. We need to know the null distribution. We can build the null distribution in our simulated experiment, just like we did it last time. We have just one population of UK mice with a given mean and standard deviation. And then we draw 4 random samples of the same size as in the original experiment, that is 12, 9, 8, and 5 mice. We calculate variance within, between, we calculate F statistic, and then repeat it again, let's say 100,000 times, and build the distribution of F. This is our simulated distribution of F, the null distribution, which represents all random samples when the null hypothesis is true. And on top of this, the black line represents the theoretical F distribution with 3 and 30 degrees of freedom. 30 comes from here, 3 comes from there. I gave you equations how to calculate these numbers of degrees of freedom. As usual, we take our observation, our observed F statistic, and put it in the context of the null distribution. And as you can see, null distribution goes to 0 very quickly. Our F is far away, probably outside the picture. And if you use PF function in R to calculate the tail probability, it will be about 10 to minus 5. It's very small, so we can safely reject the null hypothesis. There is actually a difference between our groups. This is how you can do this in R. I placed an example dataset on the web under this address, and the function read table in R can read directly from the URL. This what you can find inside this file. There are many more rows here, so I only show top of them. There are 2 columns. One is called country and another is called mass. Now you need to build a linear model. I will devote an entire lecture to linear models later, and then I will explain in details what that actually means. But what we are doing here, we are building a linear model of mass versus country. We want to see how mass depends on the country of origin of each mouse. And once we have this model, we can do Anova on the model. The top row represents variance between groups. It's this number, 207. The bottom row represents variance within groups. And this is our F value, F statistic, and this is the P value. It's exactly what I showed you before, doing this step by step. What does it really mean that there is effect as opposed to if there is no effect? This figure shows 2 cases. On the left, there is a strong effect. This is our original data. The difference between groups is in excess of the noise within each group. Particularly, you can see it in Northern Irish mice. It's really different. In the second case, on the right, the difference between groups is consistent with the noise within each group. you can imagine that each of these groups comes from the same population. It's just a different selection of data. And in this case, p-value is large and F statistic is very close to 1. On the left, there is effect. On the right, there is no effect in Anova. We have to now go through a few assumptions which are necessary before you perform your Anova. First of all, you can read it in any textbook. It requires normality. Data in each group should be distributed normally. However, Anova is quite robust against non-normality, just like a t-test. If your data are strongly not normal, like log normal, you should transform it to normality. And if this fails, you can use a non-parametric Kruskal-Wallis test. I will talk about it later. The second assumption about Anova is independence. Your groups should be completely independent. What is dependence? For example, observations of the same subject over time course. In such case, you cannot use Anova. Each group in Anova should be completely independent experiment. And the third assumption is equality of variances, that groups are sampled from populations with the same variance. Sometimes it's called homogeneity of variances or homoskedasticity. If you see this term homoskedasticity, that means equality of variance. And again, if you decide that your variances are not equal, you can use Welch's approximated test. I will show you in a moment. The normality assumption is sometimes exaggerated. My recommendation is that you should not perform normality test before Anova. I have seen requirements from some reviewers of papers. They say, oh, you have done Anova, but did you check if your data are normally distributed because it is required? No, I would say no to this. You should transform data into normality as possible. The problem with normality test, for example, Shapiro-Wilk test, or there are a few other tests for normality. First of all, it is underpowered for small samples. If you have, let's say, 8 or 10 data points, this test will provide lots of false negatives. In most cases, it tells you you cannot reject the null hypothesis, but it's because it's underpowered. On the other hand, when you have lots of data points, like hundreds, the test becomes oversensitive and it creates lots of false positives. And nothing in nature is exactly normal. So if your sample size is large enough, the test will detect departures from normality, which are real, which are statistically significant, but which do not affect Anova at all. If a reviewer still asks you to prove that your data are normal, you can throw at them a few papers showing that Anova is very robust to non-normality. How do you check if variances are equal? In most cases, it's not necessary. Again, for small samples, that will be underpowered, but you can do this. There is a test where the null hypothesis is that all variances are equal. And it's exactly like Anova, but except of measurements, XGI, we replace them with residuals, and they can be calculated with respect to the mean or to the median. And there are two different tests, but they are very similar to each other. And you have test statistic, which is the ratio of variances. So you can check whether your variances are roughly equal. In case of our mice, the test statistic is 0.93. It's distributed with F distribution, and the p-value is 0.44. So we find no reason to reject the null hypothesis. Our variances are fine. If you discover that variances are not equal, and I mean they are strongly non-equal, then there is a test developed by Welch. This is the paper. I will skip the details, but there is just a comparison for our mice data. The top row is the result from Anova. The bottom one is Welch's test, which is a corrected Anova for homoskedasticity, and they bring both very small significant p-values, so there is absolutely no difference here. This is how you can do this in R. It's not in base R. You need to find a library that does it. I found one which is called Lawstat, and you can do leaven test. which actually is Brown four-side test, and it just tells you that p-value is 0.44. But if this p-value is very small and you suspect that variances are not equal, you can use this test. It's from the same library. It's called one-way dot test, mass versus country, and it immediately does Anova with Welch's correction, and it gives you this p-value. When you do your Anova, you will only find whether there are differences between groups, but you don't find where these differences are. And there are ways of doing a more detailed analysis, just as I showed you before with chi-square test. You can do a similar thing in Anova. One of the commonly used post-hoc analysis is Tukey's test. It is essentially a multiple t-test between all pairs, and it finds differences and p-values, and these p-values are corrected for multiple tests. So if you perform this test, you get essentially a table like this, which will show you the effect size from the given pair, the difference between a pair of countries here and a corresponding p-value. And you can see that maybe Northern Irish mice, they are different from everything else, so they stand out. You can do this in R, like this. There is a Tukey HSD test. You first perform Anova, then you use the result of Anova on this, and it will give you a table like this with differences between each pair, lower and upper confidence limit, which is a 95% confidence limit of this difference, and the adjusted p-value. This can be useful. You can even make a plot of this pair versus difference, lower and upper limit, and see what they look like. And then you can look at p-values. Now, 2A Anova is, well, it's a little bit more complicated, so I want to spend more time explaining this. 2A Anova is an extension of one-way Anova where we have two independent variables. In this case, apart from the nation, we also have a fair color of the mouse. I'm afraid now we need to do some maths. Anova can be understood as a linear model. I said already there will be an entire lecture about linear models, so this will come quite handy later. One-way Anova, it's fairly simple. You can explain it by equation on the left here. There are several experimental groups or conditions, each of them containing replicates. And the measurement in group I and replicate R can be represented as the group mean, which is the same for each element in the group, plus a random noise term. And the null hypothesis is that all group means are equal. This, I hope, is fairly straightforward. Alternatively, this is more complicated, but actually more useful. Alternatively, we can use this equation on the right. It's the same equation as on the left. There are two alternative ways of looking at Anova. In this case, our result, our measurement, is the sum of the total grand mean, the group effect, and the random noise. If all means are equal, that's our null hypothesis, then obviously all these group effects must be zero, because then all the means will be equal. So this is the new null hypothesis. All alphas are equal zero, or you can use a more concise mathematical notation. For each I, alpha I is zero. These are two alternative ways of describing one-way Anova as a linear model. This is the linear model for two-way Anova. In the simpler notation, you have a measurement for a column I, row J, and replicate R. This is our table with rows and columns like countries and color of the fur of a mouse. And simply, this is the mean of this cell and a noise term. But this notation, it's not very useful. We prefer to split it into different components. There will be effect from the ground mean. This is our baseline. We measure everything with respect to this. Then there is a column effect. How much a given column in the table affects the final result. Row effect, And then there is this interaction term. I will try to explain it in details a bit later. And the noise term. Now, to make things more complicated, there are three null hypotheses in two-way ANOVA. You cannot avoid it. If you perform two-way ANOVA in R or any other software, it will return three effect sizes and three p-values. So we need to understand what they mean. They are shown here. The first null hypothesis is that column means are equal. That means there is no column effect, just like in one-way ANOVA, all alphas are 0. The second null hypothesis is that row means are equal. There is no effect from the row, and then we require that all betas are 0. And finally, the third null hypothesis is there is no interaction between rows and columns. All gammas are equal 0. This is just a pure mathematical notation, but how do we understand this? And in order to explain all these intricacies of a two-way ANOVA, we need more mice. So we introduce a second variable, fur color. We have white mice and we have black mice, and they come from 4 different countries again. And these are the results for all mice: white, black, English, Scottish, Welsh, and Northern Irish. The best way of explaining the two-way ANOVA is to visualize it. And I strongly suggest you make a similar plot yourself before you even start calculating ANOVA. It helps understanding your data. On the left, we have all data in a grid. The columns are countries, the rows are fur color, and the dashed horizontal line corresponds to the ground mean. You can see how individual results differ from this ground mean. On the right, we have summary of data. This is a very useful way of presenting ANOVA. Each point represents the mean of one cell in the table. There are 8 points, and there are 2 possible representations. On the top plot, it's represented as a function of the country, where the lines, 2 lines, correspond to black and white mice. At the bottom, it's presented as the function of white and black colors, and each line corresponds to a different country. These are exactly the same data plotted in the top and bottom panel, just presented in a different way. This is how you do a two-way ANOVA in R. You can read data from this URL. This is the data specifically for a two-way ANOVA. The second line of the code builds a linear model. And this linear model is a little bit more complicated because we say that the mass depends on the country, on the color, and also on the interaction between these two. And then you take the result of this model and call the function ANOVA. And as you can see, we have 3 F values, 3 test statistics, and we have 3 p-values. One is for country, another is for color, and the third one is the interaction term. Okay, one of them is statistically significant, other 2 are not. What does this really mean? I'm going to show you examples of data breaking each of the 3 null hypotheses. But first, a data set which is completely consistent with all 3 of them. We generate these data according to this formula. This is our linear model. The measurement is the sum of the ground mean. This is just a constant represented here by the horizontal dashed line. Then we add the alpha, which is the column term, then the row term, interaction term, and noise. Noise is a random variable. I use the random number generator in R, which is called R norm, and all these are constants given here in these matrices. In this particular case, all alphas, betas, and gammas are 0, which means there is no effect of columns, there is no effect of rows, and there is no interaction. You look at data and you see all groups look pretty much the same. There is just random variation within each group, nothing else. When you look at the summary, the lines are parallel to each other, and they are very close to the ground mean. If you perform ANOVA on these data, you get 3 large p-values. There is absolutely no effect here. This is an example where columns and only columns are not equal. Now we introduce alpha, which is for the first column is 0, for the second column is 10, for the third column is minus 10, and for the last column is 0. And you can see the effect here. The first and the last column are distributed around the ground mean, while these two are shifted up, these two are pushed down. But the way it's built, there is no effect of rows because these two tens, plus and minus 10, they cancel each out. In the summary plot, you can see that the lines are parallel to each other, but you can also see differences between the 4 nations, English, Scottish, Welsh, and Northern Irish, or here, because each colored line is a different nation. If you perform ANOVA here, you will find that the p-value for columns is very low. We can reject the first null hypothesis, but the second and the third null hypothesis they do stand. We do not reject them. This is example where rows are not equal. We do a similar thing like before, but now our betas are plus 10 and minus 10, which results in the shift of white mice, all of them up by 10, and shift of black mice, all of them by minus 10. The lines in the summary plot are still parallel to each other, but they are shifted with respect to each other. And the second p-value is very small. Rows are not equal. Okay, this is a very contrived example demonstrating the interaction effect and only interaction effect, nothing else. It is very unlikely you ever see this in nature, but it should help you understand what the interaction is. We set gamma matrix, as shown here by these numbers. In the first row, it's minus 10, plus 10, and then zeros. So we shift this one by minus 10, the second cell by plus 10, and the third and fourth cells are 0. And the opposite thing we do in the second row, where this one is shifted by plus 10, this is shifted by minus 10, and these two are 0. Because effects of rows and columns cancel each other, the only significant p-value is this one for interaction. And in the summary plots, you can see that the lines are not parallel. This one goes down and up, this one goes up and down, and these lines go in, all of them go in different direction. When you make summary plots like this, if lines are not parallel, this is the sign of interaction. Interaction means that your subjects respond to the variables in different way. White and black mice respond differently to their national origin, and mice from 4 nations respond differently to the fur colors. When lines are parallel, they respond in the same way and there is no interaction. When lines are not parallel, that means that you have some interaction. Have a look at one more example. It might explain things a little bit better. We measure effect of a drug in male and female patients. Some were given drug and others were given placebo. The first panel shows a pure effect of the drug. There is no difference between male and females, both in placebo and in the drug, but there is a strong observed effect of the drug. The second panel shows the combined effect of drug and gender, but no interaction. There is a difference between males and females. Females have higher score than males. There is also a difference between drug and placebo. Drug has a higher score than the placebo. But the difference between drug and placebo is the same in males and females. That means there is no interaction here. Both males and females respond in the same way to the drug. And the last panel shows actual interaction. Males respond stronger to the drug than females. There is a difference between males and females. There is a difference between drug and placebo, But because males and females respond differently to the drug, there is also interaction. Interaction is the combined effects of two variables. Well, I hope that helps with Anova. Before I finish, I just want to quickly mention time course experiments because sometimes these are confused with Anova and people tend to use Anova with time course experiments, which is incorrect. Imagine a time course experiment, obesity study in mice. We have two groups, untreated and treated with a drug. They are shown here by different colors and symbols. We feed them a lot of food and we observe body mass difference over time, over 10 weeks. The question is there a difference between the two groups, treated and untreated? You might be tempted to do ANOVA here because you have groups, you have drug and no drug, so there are two variables. And if you do ANOVA like this, you will get a very small p-value of 10 to minus 5. However, these data between groups, they are correlated. You follow the same subject from group from time point to time point, which means you are not allowed to use ANOVA because in ANOVA, each cell should be an individual experiment, independent experiment. You cannot use ANOVA in this case. That will be completely wrong. What can you do? Well, there are a few approaches that you can apply. The simplest way is just to do a t-test at each time point and compare the two groups. It works well. You can present it in this plot where you show logarithm of the fold change between the two groups and the logarithm minus logarithm of p-value. If you put a significance limit here, you will find that 3 points stand out above this limit. The problem with this approach, it misses point-to-point correlation because these data grow or decay as a function of time. We treat each point completely independently here, so we lose some information. You can transform your data. This is the original data. You can, for example, find the mean and the standard error for each group and just make this plot and claim that these data diverge here after about 5 weeks. Because this is a change, it's a relative change with respect to the original data point. And as you can see here at the beginning, these mice had already different body mass. So perhaps it would be good to normalize it to this particular point. That means for each mouse, you divide the mass at a given time point by the time point 0. This is the normalized body mass. You can see clearly two different groups, and you can also calculate mean and standard error and see how these two groups change. If someone asks, then you can add additional t-test later and say there is a huge difference. These two groups diverge and behave in a very different way. A better approach would be to build a model of data. Unfortunately, there is no one general way of doing this. It's strongly data dependent, and some of data sets might be used with a model, others are not. First, you need to understand your data and see how it behaves. The idea is to build a model and reduce all the time course curves to just one number, and then you can compare these numbers using, for example, a t-test. One example, it does not necessarily work with all data, but you might find the area under each curve, like this one, the bottom curve here, and you find the area under this curve. That would reduce all these data points to just one number. You can do a partial curve only later, just to stress the difference between them. And if you do this, you can get results like this. The first plot shows the area from 0 to 10 weeks for each mouse, and they are shown here for control and treatment. And the difference is not huge. The p-value is not 0.051, so we cannot really reject this. But if we look only at data from 6 to 10 weeks, later data, the difference is much more pronounced. The p-value is not 0.01. For comparison, we can do early data from 0 to 5 weeks, and there is absolutely no difference. And that tells us something about your data. There is no difference between mice early and then they start to diverge. But as I mentioned, it doesn't always work. If your curves are like this, one goes up, one goes down, they cross each other, then the area under these two groups will be very similar, and yet the curves are very different. So be careful when you use this approach. And one more explanation to some questions I've been asked before. When do you use chi-square test or g-test, and when do you use ANOVA? For chi-square test or Fisher's test or g-test, you need a contingency table. The experimental outcome is a category. So you have your cells in wild type, you put them through a sorting device, and you then count them. You find that a cell is in G1 state or S state or G. This is the outcome of the experiment. And in the table, you count all these outcomes. ANOVA is where the experimental outcome is a measurement. You do a measurement in each group. It could be counts, but there is a difference between contingency table with counts and a measurement table with counts. This table contains measurements in 3 replicates, and then you can do ANOVA. Have a look at this example. Imagine you have a bacterial antibiotic resistance test. You have 4 strains, wild type and 3 knockouts, and you grow them in normal medium and true antibiotic concentrations when you do dilution plating and count your colonies. You have a table which contains counts in 3 replicates. You might be tempted to use a chi-square test or g-test here. However, the outcome of the experiment is a measurement. It's a you measure count. This category is not the outcome of your experiment. You set it, you put it in 3 different plates. So the outcome is a measurement. That means this is not the contingency table, and you should use ANOVA in this particular case. Okay, well, that's everything for today, and thank you very much.